EDX called Pure Vectors 3 Equations of Planes. The equation of a plane using the normal to the plane. We saw in an earlier video that the scalar product of any two perpendicular vectors is 0, and we can use this relationship to define a plane by making use of a vector that is going to be perpendicular to the plane. This may look unusual to begin with, but it is very easy to work with once you get used to the new ideas and notation. So the normal vector of a plane. Every plane has a unique direction that is always perpendicular to any line that can be drawn on the plane. So a vector that is perpendicular to the plane is called the normal vector, and it is usually denoted by little n. An equation for the plane can be written if we know any single point on the plane and the normal vector. And we're going to look at a GeoGebra file that will demonstrate this detail. So here we have a point A, which we know is on the plane, and we have this normal vector going from A to B. And I can redefine this plane or create a new plane. I can move my point on the plane. So if I move A, I can create a new plane. I can also create a new plane if I change the normal vector. So we can create a unique plane if we know the normal vector to the plane, or we change the position of a point on the plane, A. Both are needed to define the plane. The interesting thing to be aware of here is if you look at the coefficients of x, y and z in the plane, they will represent the coordinates of the normal vector. So if we start moving the plane around, the normal vector, the components match the coefficients of x, y, z. So the normal is needed to define a plane, and a point on the plane is also needed to define a plane. So the vector equation of a plane using this normal vector. So the point A has a position vector little a, and we know the position of point A. That will be given. If P is some general point which is moving around the plane with coordinates x, y, z, then the position vector of P is usually denoted by little r. And if we look carefully at the diagram, the vector r minus a and the normal vector n will be perpendicular to each other. Hence the vector equation of the plane can be written as r minus a dotted with n must be 0, or it's more usually remembered as r dotted with n equals a dotted with m. There's an important little detail here. Once we dot a with n, remember a is a known position vector and n is a known normal vector. Once we dot a with n, we get a constant, and EDX will refer to that constant in their formula book and notations as k. So you can use r dot n equals a dot n, or once you've dotted a with n, you can think of it as r dot n equals a constant k. So this is just explaining that in a bit more detail. So we can see the vector from a to r is definitely perpendicular to the normal, and the vector from a to r is r minus a. And if we dot that with n, we get 0. And if we expand the brackets, we will get r dot n equals a dot n, which equals constant k. So this is an extract from the EDX specification, and you can see here that they are using r dot n equals k to represent the equation of a plane. And we can see here that we've got a different constant d defined in this notation as n1x plus n2y plus n3z plus d equals 0, where n1, n2, n3 is the normal vector that we've been looking at on GeoGebra and mentioning in the video. So here we're going to find the scalar product form of the plane, which definitely goes through the given point A, which is at 1, 2, 0, and is perpendicular to the vector 2i plus 5j plus 3k. I would strongly recommend, once you have identified the normal perpendicular vector, I would give it the name n. So n is 2, 5, 3. Our position vector of a point on this plane is definitely given, and I'm going to call that A, 1, 2, 0. And now I'm going to use R dotted with the normal is a known point, A dotted with the same normal. So R is my general point, dotted with the normal, which is definitely 2, 5, 3, is a known point on the plane, which is 1, 2, 0, dotted with the same normal, 2, 5, 3. So R dotted with 2, 5, 3. So now I'm going to do the dot product on the other side. So that's 2 plus 10 plus 0. So I'm going to leave this in the required scalar product form of R dotted with 2, 5, 3 is 12. And 12 here is the constant K that they will refer to in the specification. So you can just see a little bit more clearly the method we've just been using. In the next session we're going to be looking at the equation of a plane given in Cartesian form.